Let's solve another problem where we're asked to calculate the entropy change during the process. And this time, we'll be using a gas in the process, and we'll solve it two different ways. One way involving constant specific heats. 5 kilograms of nitrogen undergoes a process from P1 equals 5 bar, T1 equals 400 K, to P2 equals 2 bar, and T2 equals 500 K. Assuming ideal gas behavior, determine the change in entropy in kilojoules per degree Kelvin with A, constant specific heats evaluated at 450 K, and B, with variable specific heats. Let's lay out a storyboard for this problem. I can't draw a schematic because no information about the process hardware was made available. It simply says nitrogen undergoes a process. So we'll simply define the nitrogen molecules as our system, but we don't have a schematic for that. We do have some given data. We know that the mass of the nitrogen in our system is 5 kilograms. We know the molecular weight for N2 is 28.01. And as previously stated, state 1 and state 2 are both defined by given temperatures and pressures. We're going to model this as a closed system. There is no significant change in kinetic or potential energy, so we'll regard them as having a value of 0. And we will treat the nitrogen as an ideal gas. So the first problem we want to solve, we're going to solve with specific heats. So instead of getting S0 values from a table at various temperatures, I'm just going to get specific heat from a table known as the ideal gas specific heats of some common gases. And in there, we'll find that the specific heat of nitrogen at 450 degrees Kelvin is 1.049 kilojoules per kilogram K. Now we're going to use this expression for delta S because we have constant specific heats. We're not going to use S0 values. Here we're going to use the value of C sub P. And we know that delta S is C sub P times the natural log of T2 over T1 minus the gas constant for nitrogen times the natural log of P2 over P1. So let's find the gas constant for nitrogen. The nitrogen gas constant is the universal gas constant, which has a value of 8.314. We'll divide that by the molecular weight of nitrogen, which is 28.01. And that quotient has units of kilojoules per kilogram K. So the gas constant for nitrogen is 0.2968 kilojoules per kilogram K. Well, now we can calculate the change in specific entropy. It's just C sub P times the natural log of T2 over T1 minus the gas constant times the natural log of P2 over P1. Well, we found this value of C sub P in the table. We were given the temperatures of T2 and T1 as 500 and 400 K respectively. We just determined the gas constant for nitrogen, and we have the natural log then of P2 over P1. We calculate that the change in specific entropy during this process is 0.5061 kilojoules per kilogram K. Well, now we're asked to find the change in entropy in units of kilojoules per kilogram, or excuse me, kilojoules per degree Kelvin. Well, that's, large delta S. So the change in entropy is the mass times the change in specific entropy. So we'll multiply the mass of 5 kilograms times the change in specific entropy that we just calculated. And we get the change in total entropy is 2.531 kilojoules per degree Kelvin. Let's solve the problem again, only this time we will use variable specific heats. So now we're going to go back to our table for ideal gas properties of some selected common gases, and we're going to go to the nitrogen section. And we're going to get S0 at 500 degrees Kelvin, and we're going to get S naught at 400 degrees Kelvin. But in air, they gave us those values in kilojoules per kilogram K. But for the other gases, we're getting values of S naught in kilomoles. So we have to be careful of our units here. We're going to be working with kilomoles until we decide to convert that to kilograms. So let's substitute. We're going to substitute values into this expression. Again, we have delta S is S naught of T2 minus S naught of T1 minus R natural log of P2 over P1. So delta S is going to be S naught of T2, which we got as 206. And we're going to subtract S naught of T1, which is 200.07. But those have units of kilojoules per kilomole K. So I'm going to subtract from that R natural log P2 over P1. So I'm going to use the universal gas constant R because it has units of kilojoules per kilomole K. And then I have to multiply by the natural log of P2, which is 2 bar, over P1, which is 5 bar. So that gives me a value of delta S is 14.1770 kilojoules per kilomole K. Well, now I'm going to convert the mole unit to mass units. And I'll do that by dividing by the molecular weight, which has a value of 28.01 kilograms per kilomole. So I'm going to write that this way, and I calculate now that delta S is 0.5061 kilojoules per kilogram K. It's exactly the same value we got before. And to get the entropy change, we'll multiply the specific entropy change by the mass of the system, which was 5 kilograms. And once again, we get that delta S is 2.531 kilojoules per degree Kelvin. Now, we get excellent corroboration here. We know that using variable specific heat, that is to say using table values, is the most accurate way of calculating the change in entropy. But using constant specific heat, we got an excellent answer. And that is because we had a rather small temperature change during this process. It only changed by 100 degrees Kelvin, which is 100 degrees C. And during processes that have temperature changes of less than 200 degrees C, we can get excellent results using constant specific heats. Now, and some gases we can go even higher than that, but it depends on the gas. But here with a small temperature change and where we use the value of C sub P that was taken at the average temperature of this process, you can see that we got an excellent result. So let's draw a TS diagram of this process. State 1 for the nitrogen gas was at 400 Kelvin and 5 bar. State 2 was at 500 Kelvin and 2 bar. And we can see clearly that the entropy at state 2 has a higher value than at state 1, and therefore our delta S came out positive.